Hey, so this week I got a bit more progress done on my Something Awesome project. The main sort of areas that I've been exploring has been hooking, so hooking system calls, and then also playing around with intercepting network packets and using sort of different malicious things there. So I have a little demo this week of sort of the progress I've made. But I just want to talk first a little bit about sort of the issues that I've come up with. And the first sort of, I guess the biggest thing has just been that the book I've been sort of following along is sort of quite old now. It was created maybe I think it was written in 2006 or something like that. So there's quite a few sort of variations and differences between FreeBSD between now and then. The main issue I've been having is kernel panics. So on the old, I guess, when you think about writing C code, if you get a segmentation fault, it's sort of annoying, but it's not a big deal because your program just crashes. With this, if you make a mistake or dereference a null pointer or have a page fault or anything like that, the whole operating system crashes. And it's kind of a bit slow to reboot. So you sort of don't want to spend a lot of time just doing the same thing over and over again, trying to find the bug. You really sort of want to be better at reading code and reading manuals and that sort of stuff. So I'm just going to walk you through the little bit of code that was causing me issues. And this was something that used to be able to be used to move data from a buffer and kernel space into, I guess, just user space. And it took me quite a while, reading manual pages and all that sort of stuff to actually find this issue. But then sort of reading the manual pages, I found that I needed to use a different function. And once when we got to there, it was actually quite easy to get through after that. And I sort of guess I'm just going to finish off with a demo of the code now. Okay, so previously I was using a Raspberry Pi to run FreeBSD on. I've changed that, and the reason I've done that is because of the kernel panics I was talking about. So anytime my operating system crashed, because I had a bug in the module I was writing, I'd have to get up from my desk, go to my router, which is in another room, unplug the Pi, plug it back in, wait for it to reboot. So working with a virtual machine is quite a fair bit easier. So as you can see here, I have Kali running and FreeBSD running. So for most of the stuff I do on FreeBSD, I run through like a non-root account on Putty over here. And on the right, I've got my instance of Kali. So at the moment, our rootkit is sort of comprised of two programs. We have a kernel module that intercepts internet packets, and we have a program that runs in user space that we use to spawn a remote shell when the right packet works. So we'll be going through the code after this, but this is sort of just a demo of what I've got at the moment. So I start the spawn shell running, and what this program does is it just waits and it constantly reads a device, and if the right packet is coming, then it launches a shell. So that's been pre-programmed with the IP address of this virtual machine, and we just use netcat and we just wait. That's all we do, we just listen on it. I then use Nemesis to send this icmp packet over, and as you can see, it'll take a couple of seconds, but then we get this launching shell, and you'll see here a shell has popped up of that BSD program, and we have access. At the moment, this isn't running in root, but we can repeat this if we come over here and run this as a root user. So if we just do the shell again, listening on that port and just sending it again, have to wait a little bit, and we get this with root. So this is pretty cool. At the moment, it's still very easy to detect. So what I'll be doing is writing like a shell script that will sort of install all of this sort of stuff as root and we'll be doing that probably over the next few weeks. But this is really where I wanted to get to for credit, just be able to have a rootkit running, which gives me a remote shell into the operating system. So let's take a look through the code now that actually does this. Okay, so really the last bit of this is just the walkthrough. So at the moment, we have sort of three things in our directory. We have a makefile that's used to create the rootkit, as well as spawn, which is the user space program that actually spawns our shell. This is something that you'd be able to run on your own machine if you had FreeBSD by just typing make, and it will create everything. If we start from the top of this file, there's quite a few includes. You probably don't need all of these. And I also have this trigger. So this is the what the content of the packet needs to be if you want to trigger that shell to be created. The first things we have is a lock, which we use to ensure mutual exclusion in our kernel space program. We have a buffer. This is what we write to. It's currently 256 bytes. Doesn't need to be that big. We also have this device struct. So we actually register a device which we'll then need to hide later on. So here we give it sort of the function pointers that we have. So open, close, read and write. Those are the only things we support. And if you look at it, open and close don't actually do anything. It just returns 0. So they just work correctly, essentially. Read, what read will do is it will get mutual exclusion on the buffer, and we then copy across the data that lives in buffer into our UIO, which is then sent to the consuming program. We then clear the buffer and we release the lock. This device is read-only, so we don't do anything for writes. And then we have this exec-v hook. This is really just something that has been used in a previous sort of example I was going through in the book. We will be seeing this again later though, as this is what we're going to use to hide the spawn program from users, I guess. This is really sort of where we start to get exciting. This is the icmp hook. So this is going to hook any icmp packet that comes in from the machine. We muck around with it to retrieve the data that we're interested in, and then we restore back the data from before we received it. And this way we can pass it on to the regular icmp handler, and anyone else sort of trying to discover our rootkit is going to be none the wiser. If the data is correct and it contains the icmp data is the same as our trigger, which is go_root, what we then do is we come in here and we copy across that trigger into the buffer so that the spawn program can then read the device that we've registered and spawn the shell when that packet is received. We then just let the regular icmp input handler handle it. What we probably want to do here instead is return 0, and that way our dodgy packet never gets received. Down here is the load. This is a module that just gets, or a function that gets used a lot anytime you want to create a kernel module. And here, this is what happens when we load it into the kernel. So we create the lock, we set our buffer with just null terminators, and then we override so that instead of calling input icmp input, it'll call our input hook. We then also make our device. We let anybody read it or write it, and at the moment it's called remote. So here you can give it a less suspicious name, or you could even hide it from anybody else trying to access it. And that's probably what we'll do in future. Just unload is just the reverse. It just restores everything back to how it should be. And then we register it with the operating system down here. The spawn program is even simpler. We have our main down here. And this is just an infinite loop. It runs the execute step, it sleeps for 6 seconds, and it repeats like that forever. Here, we try to open that dev remote, and if we can't, we just say file not found. We try to read from it up to 512 bytes, which is way larger than what we need to. And then we compare it. If the data that we received is go root, we then reset our buffer, and we call the evil function, which is at the top of the screen. All this does is it forks the process, it launches a shell, and this is the sort of the bit that gives us the reverse shell. So here, I send it out to the IP address of Calais with listening on port 444. At the moment, this is super easy to find. In future weeks, I will be, doing more things with my rootkit to hide all of this extra stuff. But that's really just a walkthrough of what I got done this week.